Hi everyone, Daniel here. We're going to start the COM 3010 lecture with something very simple today. We're going to be talking about problems and algorithms. You might go, wait, what? We're in third year. Why are we talking about problems and algorithms again? This is something we should be doing in COM 1000, right? Well, the thing about COM 3010 is that we're going to be doing a few things that you've done before. If you look at the topic list, you will see that there are a few COM 2010 topics that we're going to be doing again in this unit, because the idea is we're going to do them more rigorously. All right, so let's get started. Going to talk about algorithms, going to talk about problems. I'm going to talk about why you want to study algorithms again. Really, it's going to feel like a first year course again, which is great. So let's start with algorithm. What is the definition of an algorithm? I got some definition there from the textbook, so I got them from the Wikipedia. Simplest one there says that an algorithm is a procedure, it's a series of steps that you take to accomplish a specific task. Wikipedia, well, it's a bit more wordy, but pretty much to say the same thing, right? Just a bunch of instruction that lets you do something. Now, there's a third definition there, CLRS. If you don't know already, CLRS is your textbook. That acronym I'm gonna use again. I'm gonna use it quite a few times. Basically, every time you see CLRS on the lecture slides, that means the textbook. Look on Ireland if you need more information. Anyway, the definition of CLRS says that an algorithm is a well-defined computational procedure that takes some value as input and produces some value as output. So that's probably something slightly different to what you're used to. You've probably never heard of this definition of algorithm before. And in this lecture, this is what I want to explain, like how to see algorithms as something that maps inputs to outputs. Right? It may sound a bit weird, but anyway, definitions are not important. It's more important that you understand the concept. I'm not going to ask you like definition questions in the exam for sure. So just make sure you understand concepts. Don't worry too much about the definitions, like the exact wording, right? And what do we use algorithm for? Well, obviously we use algorithms to solve problems. Computational problem. I have a definition there for computational problem. It says that if you have a set of inputs and a set of outputs, then a computational problem specifies the desired relationship between the two sets, between the input and output. So there it is again, this input and output thing. This is one aspect that I want to push onto you today. I want you to be able to see algorithms and problems in terms of inputs and outputs. We're going to be talking about a few examples today. I have three in particular. The first one is simple. If I give you an array, go find the largest value in A. Second one, I'm going to give you an integer n. Go find me the non-trivial prime factors of n. And the last one is a bit more difficult. I'm going to give you a map with n cities, and I'm going to give you the cost of traveling between each pair of cities, and now I want you to find me the cheapest way to go from A to B. So you may already know that this is called the traveling salesman problem. Okay, so let's work with those three problems. Just keep them in mind for now. Now, computational problem. What do we even talk about it? Well, like I said, I want to give you a different point of view. Maybe you already think like this, which is great. That's fine. But you haven't. Hopefully this introduces a new way of thinking about problems. So let's look at the first problem. If I give you an array A, go find the largest value in A. So you see that, and maybe an example pops up in your head. You see, I have an array there, 5, 1, 7, 2, 6, 9, 11. Go find me the largest value, you're just going to have 11. So if I give you an array, well, that array there, you're going to give me 11. Right? Now, here's the thing. You are used to seeing these kind of questions in COM 1 to 5 or COM 1010. So if I ask you to write the code that returns the largest element, you're probably going to assume that you're going to get an array of integers, right? But the question is just saying, if I give you an array, then give me the largest element. And there can be many different kind of inputs. For example, I can give you an array of strings. I can give you an array of nulls. I can even give you an empty array. Even if I give you an array of integers, I can give you an array which is sorted in descending order, an array which is sorted in ascending order, an array of when you have all ones, all the same value. And each one of these inputs will make you write the solution differently, right? If I give you an array, if I tell you the array is always sorted, then you would write it differently, right? Because the largest element is going to be in one end of the array. So that's my first point here. A computational problem should have a well-defined input, including any constraints. So constraints are just extra conditions you want to put on the input. For example, input is in a set of integers, and you can say, well, it's actually a set of odd integers, so that's a constraint, for example, right? Plus, if you define a problem, you must have a well-defined output and how the output relates to input. So what we had earlier, given an array A, find the largest value in A, that's kind of bad. A better way to say that would be, given an array of integers A, find the largest value in A. Well, or find the largest integer in A, I should say. There, it is clear that the input is an array of integers. The output is also well defined because you know what integers are. You know what the largest integer means because you can compare integers. So that's a better definition of the problem. So what I'm saying here is that the first step in solving a problem is to understand what the problem is. And if you want to understand the problem, you have to understand the inputs and how the output is related to the input. So don't start solving a problem until you understand it. So what about this one? If I give you a positive integer n and ask you to find the prime factors, do you think this definition is clear enough? Can you start working? Can you start writing a code that does this? I think it's clear enough. Like, you know, the input is going to be a positive integer, so that's pretty clear cut. And you also know what you need to output. Well, you might want to ask, like, how should I output it? That's going to be an array or just a list or whatever. But those are trivial stuff that we can worry about later. The most important thing is that you know how to perform the calculations. If I give you the input, you know how to produce the output. Same thing with the last example, the last problem example. If I give you a map with n cities and so on, the traveling salesman problem, what are your inputs? A map with n cities, sure. You need to know how they're connected. So you expect some sort of graph maybe. You must know the cost of traveling between any two cities. So you need the weights of the edges to be the costs. And you need to know which cities, A and B, like which cities you have to compute the distance from. Okay. And hopefully the output there is pretty clear enough. You can work it out. So again, clear input, clear output. These are the things you look for when you're trying to solve a problem for the first time, right? You have to have a clear input and a clear output. So that's pretty much what I said there. You know, the set of inputs and set of outputs and how to link them. And these are examples of, well, these are not computational problems. If I just tell you, go find the best place in Australia. Why is that a bad problem? Because you don't know what the input, you know what the output is. Like, what is a place? A city, a beach, a bar? What does best mean? How do you relate the inputs? Even if you work out the inputs, like a place, if you work out what a place is, how do you know that it's best? How do you quantify a place? Another one, if I give you a set of triangles, sort them. All right, the input can be clear. Like, you have a set of triangles, great. Maybe it's a set of like the height and the base, like the side of the dimension of triangles. Sure. Now, if I ask you to sort them, you're gonna go, how do I sort them? What do you mean? How do I compare to triangles? If I have two different triangles, how do I tell which one's bigger, which one's smaller? So the question doesn't specify that. And if this is not something which is like obvious, then they just mean that it's a bad problem. So again, every time you see a problem, the first thing you do is go find the proper set of inputs and go work out what output you should produce and how you link them. Now here we have the first problem. Oh no, sorry, this is the finding the prime factors. This is how I see the relationship between input and outputs. Like, this is a problem, right? The problem here is finding the prime factors. So 15, the prime factor is in 25. So I map 15 to the array containing 3 and 5. So 16 only has one prime factor, 2. So 16 will map to 2. So that's 2. 2 will also map to 2 because, again, the only prime factor is just 2. So see how I'm doing, I'm trying to explain how to focus on the input and the output. So if the set of input is clear and the set of output is clear, I can link them together. This is how I see problems, and this is also how I see algorithms. Is that good enough, by the way? This is the first one. Like if I give you an array of integers, so see I modified the definition here. If I give you an array of integers, go find the largest integer in A. I should say largest integer in A, really. So again, I have the inputs on the left hand side and I have the outputs on the right hand side. I mean, there can be many outputs and there can be many more inputs. You gotta think that there's like an infinite number of like inputs here. Like there's an infinite number of arrays and there's an infinite number of like integers on the right hand side. So yeah, this is mapping input and outputs. Does that look good enough to you? Hopefully, great. Well, it's kind of missing something. This one. If I give you an empty array, what should we do? So anyway, the hope is that you can kind of see problem as set of inputs and set of outputs and how you relate them. And please be careful when you do that. Like make sure you take into account every possible inputs and you also take into account every possible outputs. Well, the output can be nothing, by the way, sometimes, because sometimes there is no solution, in which case it will map to nothing. Now, a particular input to a problem is referred to as an instance of a problem. So on Wikipedia, there's actually a nice quote. It says that a computational problem can be viewed as an infinite collection of instances together with a possibly empty set of solutions for every instance. So that's how I see like input. You got like infinite number of inputs on the left hand side and you got infinite number of outputs on the right hand side and you just draw arrows between them. This is what algorithm does. An algorithm, so the problem has that like relationship, or I mean a problem already knows a relationship. If you have a question, you get the answer, and the algorithm task is to find them, right? And the algorithm is correct if for every instance it halts. Now this is important. And the algorithm is only correct if it actually stops. It's correct if for every instance it halts with a correct output. Right, so hopefully that's clear to you, like thinking about problems and algorithms in terms of input and outputs. When I'm doing a problem, I like to think about input first because it gives me some idea about the complexity of the problem. Like if I think about the set of inputs, it'll tell me, all right, just how many inputs are there? How many of them I have to go through? Okay, so that's a very good start in solving problems, because you kind of know how much effort you have to spend. Now, looking at the inputs also help me optimize my solution. Like, can I ignore certain types of inputs? All right, like if I'm looking at prime numbers, can I ignore even numbers, for example, because that will cut it down a lot. What kind of inputs will I be getting? Will I be getting a small inputs all the time? Will I be getting large inputs all the time? Do I really need to optimize my code so that I can handle small inputs or large inputs? Also, the type of input will tell me what kind of data structure I can use. So these are the considerations you need to have when you're trying to solve a problem. You can see chapter 10 of Skinner. It really is only about, I think, 3-4 pages. We'll talk more about chapter 10 later. It's basically like a guide on how to solve a problem. This is something you should have as a handy guide every time you have a problem to solve. Anyway, what kind of computational problems are there? Now, these are definitions you need to know. Again, you don't need to know the exact wording for it. I mean, there's no exact wording for these definitions, right? Just know what they are. Computational problems. You will encounter something called decision problems a lot. So decision problems is a problem where you only output yes or no. So for example, I'm going to give you a positive integer. It's a prime number, yes or no. I'm gonna give you a map with n cities and the cost of traveling between each city, like the traveling salesman problem. But this time I'm just gonna ask you, can you travel from A to B? So it's more like I give you a graph. Is A and B connected? Or for less than X, actually. I'll ask you that. Again, the answer is just yes or no, right? So those kind of problems, we call them decision problem. It's easy. Well, not that easy, but at least you only say yes or no. Search problems. When you're searching, it's basically, well, you know what search problem is. You've been doing it for a long time. Find one or more output that satisfy the required relation to the input. So if I give you a positive integer n, go find its non-trivial prime factors. If I give you a map with n cities, find all possible paths between city A and city B. Searching. So you go through all the possible cases and you pick up the ones that satisfy the criteria, whatever the relationship you need. Counting problem is similar. So basically it's a search problem, but you don't actually have to, for example, like if I give you a map and I ask you to work out the number of possible paths, you don't have to give me the actual path. You can just tell me the number of paths there is between A and B. Now, finally, you will hear about optimization problems. Actually, the two most important ones here that you need to know is decision problems and optimization problem. We're going to see them later in P versus NP. So optimization is probably the hardest one. You have to find the best possible solution. So I'm going to give you criteria, and this is like pretty much traveling salesman. I want you to find the best way, the cheapest cost of going from A to B. Okay, so you may have to go through all possible solutions of going from A to B, right? And then you find one which is the best. So as you can see, if you compare the optimization problem to the other ones, this is the one that takes the most effort. Yeah. So that should do it for problems. Yeah, it's kind of funny that we're doing this in third year after you've been doing so many problems for so many years. But yeah, hopefully that gives you a new point of view, or if not, if you already know how to see problems that way, that's great. Now we're going to move to the second part of the lecture. Just going to talk about why you want to study algorithms. So there are three main reasons that I can see. This is coming from my supervisor's lecture, like maybe a decade ago. Number one is that if you have a problem, then the obvious solutions are not always tractable. So by tractable, I mean something that can be solved in polynomial time. Easy. You will see this word a lot: tractable and intractable. So this is one reason why you want to study algorithms, because if you come across a problem, you can probably always solve it just in brute force. You can just like try to compute every possible combinations, but that is not always feasible, which is why you want to learn algorithms that will try to give you a better answer, like a more efficient answer. Number two, a tractable solution can always be improved. So you get a problem, you know how to solve it, and actually you solve it pretty efficiently, but sometimes you can solve it even faster. And again, how do you gain the ability to know that? Is by learning more and more algorithms. You learn what people have done and then see if you can adapt what they've done into your problem. And finally, the last reason on why you want to study algorithms, you want to be able to recognize hard problems. So if you know the problem is hard, and we're going to talk about this, we're going to talk about P versus NP. So I think that NP problems are hard. If you know what the hard problems are, you're not gonna spend that much time trying to look for an efficient solution, because it doesn't exist. All right. So we're gonna talk about these in more details. Starting with the first one, give you examples as well. All right. Obvious solutions are not always tractable. Now, the traveling salesman question. Like I give you a map and I give you the cost of moving between cities, and I ask you, go work out the best way of going from A to B. So this is actually not a hard problem. Well, I think the way I see it, most problems are not hard. It's hard to solve it efficiently, right? You can always solve something using brute force most of the time. And let's think about how to solve this using brute force. So if you want to go from A to B, if you have no intermediate cities, like there's one possibility. So that's one possible path. You just go straight from A to B. You can also go from A to B by jumping to one city in the middle. So how many choices you have in that case? You have n minus 2 choices. Of course, you can also go to 2 different cities before you go into B. Like A, you go to another city, you go to another city, and then you go to B. So there you will have n minus 2 times n minus 3 choices. Okay. I hope you can work out how I get those n minus 2 and n minus 3 choices. Just simple combinations. So the total number of paths is okay, 1 plus n minus 2 plus n minus 3 times n minus 2 plus so on. I mean, if I have more than, depending what n is, right? Because n can be a very big number. So these terms here, it's actually represented by this formula here. And you know, notice this like factorial. I hope you know what factorial is. If you're still a bit weak in the mathematics side, you can look at the appendix of CLRS, the textbook. If you look at appendix A, B, C, there's some mathematical background that you can pick up. We're going to talk about combinations and permutations a bit later on. But for now, at least you know what factorial is, I hope. So if k ever goes to 50, 50 factorial is 3.04 times 10 to the power of 64. That's a big number. This big, right? So this kind of problem, like it sounds simple. Like I give you 2 cities, A and B. Go find the cheapest path between A and B. This is actually intractable if you try to use brute force. So you have to use better methods to try to solve it. Okay, and this is why you study algorithms. This is why you study what people have done to solve hard problems. Second reason why you want to learn about algorithms. Tractable solutions can be improved. So the idea here is that you have a problem and you know how to solve it. Well, you can still learn what other people have done to maybe solve your problem faster. So don't be satisfied just because you have an efficient solution, because sometimes it can be done better. Okay, now I'm going to use an example. So this actually, I really like this example because this happened to me. I'm going to give you a list of n integers, and I want you to find the largest and the smallest integers. So n, don't just find the smallest, don't just find the largest, I want you to find both. What is the minimum number of comparisons that you need to do? You will have to do n minus 1 comparison at least, yeah? You know why? Well, because if you have n integers, you have to look at all of them, so that's n minus 1 comparisons. Anyway, how many comparisons would you need to find the largest and smallest integers? You can pause the video and think about a solution. I mean, this is like a COM 1000 question, right? It's not something hard. This is how I would do it. I'm going to need 2 n minus 2 comparisons. So if I just want to find the largest element, I will need n minus 1 comparisons. So what I mean by that is I will assume the first element is the largest, and then I have to do n minus 1 comparisons more like, well, I will compare 44 to, well, each one of them. Well, actually the way I do it, I will assume that 44 is the largest element, then I compare 44 to 13, 22, 63, 63 is larger, so that becomes the largest element now, then I keep on comparing. So I will be doing n minus 1 comparisons. But now you want the smallest element as well, because you want the smallest element as well. Every time you arrive at an index, you might as well do 2 comparisons, right? So you will assume that 44 to be the largest and the smallest, and then you move to the next element, you move to 13, you replace the smallest with 13, and then so on. Pretty simple. I'm sure you know what I'm talking about. So if you do it that way, it'll take 14 comparisons. Now, here's a trivia. Can you do better than 14 comparisons? I mean, you can pause the video and have a think about it. See if you can find a solution better than 2n minus 2. But anyway, I'm going to show you the answer now. Yes, you can. There's a better way to do it. Okay. So for simplicity, I'm just going to assume n is even. All right. I'm going to pair out the numbers. So here's the array again. I'm going to pair them up. Now, once I pair them up, I'm going to take the largest and put it on one side, put it on the top here. So 44, 63, 93, 67. And I'm going to take the smallest elements and put it at the bottom. And now what I'm going to do is, I have an array of size 4, and on the top ones here, I'm going to find the largest element. And the bottom ones here, I'm going to find the smallest element. How many comparisons do I need? Well, 1, 2, 3, 4. And then 3 more up here, and then 3 more down there. 10 comparisons, as opposed to 14. So if n is larger, the difference is going to be bigger, because before we're doing 2n minus 2 comparisons. Now we're doing 3n over 2 minus 2 comparisons. Like this is like 3 over 2, like 1.5 n minus 2, as opposed to 2n minus 2. So as n increases, the number of comparisons you're doing is much less and less, right? So again, that example where you know how to solve a problem, and you think, oh, this is an efficient way to do it. This is already n. And then someone comes up and say, I can do better. Well, as in we also studied that problem and we came up with a better solution. So here it is. This is what you learn when you're learning about algorithms. You learn about way to solve something. So even things that you already solved, you learn new ways to do it. And finally, one big reason to learn algorithms is you'll be able to learn hard problems. Again, we talk about intractable problems. So these are problems that are hard, as in what we mean by hard is that we don't know any polynomial solution to it. So nothing n squared, nothing n cubed. So solution is going to be something like big O to the power of n. So we're going to talk about big O notations again in the next lecture, but hopefully, I mean, you already know stuff. You already know a bit about big O notations, right? So hopefully that makes sense. Now, the idea is that if you get a hard problem, if you see a hard problem, then you should not spend any time trying to find an efficient solution to it. Just recognize you should spend the time proving that the problem you have actually is hard. So the nice comic that I have, this is something I showed in the introductory lecture as well. This is one of my favorite comic when it comes to P versus NP. If you are working and your boss tells you to, the boss gives you a problem and tells you, hey, find an efficient way to do this, and you can't, well, one option you have to just go to your boss and say, look, I tried, I can't do it, I'm dumb, please be nice to me, and all that. Now, if you learn enough algorithms, if you have enough experience, you can probably recognize that the problem that the boss asks you to do is actually very, very hard. Namely, it's an NP problem. And you can actually argue that, look, there's no way I can find a good solution to the problem that you've given me, because no such algorithm is possible, right? And it's not just me saying that. All these famous people, all these scientists, there's a proof saying that this problem is hard, and I can do the work and to show you that this problem is hard. Now, this is what we're going to be doing when we're discussing P versus NP, and that's in week 11, week 12, or maybe week 13, I'm not sure, at the end of the semester. And that is the main motivation. So learning about problems which are hard is still useful. Like learning about problems which you can't solve is still useful because of this reason. Okay. So we talk about problems, we talk about why you want to study algorithms to solve problems, and I just want to close by talking about how you should study algorithms, okay, and how we're going to do that in Column 3010. So we're going to go through the theoretical foundations. We're going to do complexity analysis. We're going to do correctness analysis. Talk about this in the welcome lecture. So we're going to define terms that we need later on, like we define what a problem is, we define interactability, and you're going to learn more and more tools. You're going to learn about big O notations, you're going to learn about limit variance, and then we will go through the common problem-solving strategies. We're going to go through define and conquer, dynamic programming, greedy method. Then after that, we're going to go through different examples of algorithms, like algorithms with strings, algorithms with graphs. Okay. But most importantly is that when you see these problems, try to write your own solution to these problems, because that's the only way you can get better at solving problems. All right. The analogy that I like to use is, if you want to become a chef, well, what do you have to do? Like, do you copy other people's recipe? Like, if you're starting out, I mean, can you come up with the recipe yourself? Well, most of the time, you have to learn what other people have done, right? And you copy their recipes. You copy what they do. Do you memorize recipes? Yes and no. Like, you memorize some recipes, sure, because you need a good foundation. Like, you can come up with any kind of dish, right? But there are some recipes that you don't need to memorize, and that's okay. You just have them at the back of your mind. Like, you write them in the book somewhere, and if you need it, you bring it up. And algorithm studies like that. You're not gonna memorize every algorithm there is. Well, if you're a super genius, maybe you can, but this is not expected. It's just that you can remember how to do it, and you remember where you've read it, and you can just bring up your notes every time you need to. Do you only study recipes? Become a chef? Like, do you try to study the ingredients? Do you try to study utensils? Do you try to learn technology? Like, what new stuff can you bring to your kitchen? Same thing with learning about algorithms, right? So in this course, yeah, it's theoretical. We're gonna be doing a lot of theory stuff, even not that much programming, in my opinion. But you should also learn about your programming language, because that's a tool that you have to solve problems. Like, most of you are good in Java. That's great. Go learn Java more. Learn what Java can do. Like, how many containers do you know? Like, how many classes you actually use? Can you do concurrency in Java? Now, most importantly, the question there is, can you be a good chef if you only read and memorize recipes? So like I said earlier, it's okay if you want to memorize some stuff. So it's okay if you want to memorize some code, you want to memorize some algorithm, that's fine. You don't actually need to. But what's important is, you may not memorize how the algorithm work, but you need to know the approach. You need to know the logic behind the algorithm. Why was the solution written this way? Go find that out. Go find that out and memorize that. Learn that. Okay. Understand the logic behind the solution to a problem, because you will see that there will be many problems that have the same logic, and you will see, like, it's basically the same approach applied differently, because a lot of problems in real life is actually very similar to one another. All right, and finally, can you be a good chef if you don't cook? Probably not. So same thing, you want to learn about algorithms, you want to learn about problem solving, you want to learn how to do complexity analysis, correctness analysis. You have to do it yourself, and you have to do it often, right? So Com 3010 is a subject where you should practice as much as you can. The more you practice, the better you're going to be at it, and when it comes to exams, you will just ace it if you practice often. Okay, anyway, that's enough for me. We covered problems, algorithms. I know this lecture is probably a bit too abstract for you, nothing concrete. But yeah, the next few lectures we'll do more and more concrete stuff. Anyway, that's it for me for now. I'll see you in the next lecture.